Yeah. Hi, everyone. I work for ARM. Yeah, it's great to have you all here in Cambridge. And I thought to honor the fact that we're finally in Britain with OSPM, this talk won't actually be about SCADX and BPF scheduling, but rather SHEDX and BPF scheduling. Thank you. Yeah, I've worked with SHEDX for like the last year or so. Just played around a bit, what's possible, and I discovered some things I thought it would be reasonably interesting for some of you. So yeah, I'll also give like a brief intro. You don't need to know much about SHEDX. How BPF schedules usually look like. I've seen very little on that actually. What callbacks exist, and in particular what overhead comes with implementing that. And yeah, of course, for ARM, we looked at implementing PELT in BPF, that is, capacity-aware scheduling, energy-aware scheduling, for scheduling, that is in BPF, so the SMT security thing. Also gang scheduling, a bit getting increasingly more niche, esoteric. Yeah, there's summary and there will be a discussion. I think even if you don't care about SHEDX, which I understand some people here might not, I think I have some goodies in there that you might still like be interested in. Or yeah, I mean, maybe also this. I've not seen much actually of like how do I use SHEDX if maybe I've seen kernel code before or even kernel scheduler code before. So hopefully that will also answer some questions. So yeah, where are we today? SHEDX is upstream for a while. In particular, like the last few months, I'm sure if you anywhere on the list, you've seen that the vendors, Android vendors, have started looking into it. There's loads of patches. Yeah, as already mentioned, it is the kernel infrastructure to facilitate writing a scheduler in BPF for this class X task or SHEDX task, which is the lowest. And it comes in the form of implemented SHEDX ops callbacks that the kernel will call into. Where it executes the BPF code. Yeah, for example, ops.enqueue. Yeah, and most schedulers implement, they do this hybrid approach where, for example, they do active load balancing, which is rather rare in user space, mostly to avoid like the complexity that comes with BPF. It's a bit of a pain to implement, and obviously, if the active load balancing only runs quite rarely, yeah, it doesn't. It's not that bad having it communicate stuff to user space and back. That also means that most schedulers actually keep the wake up rather simple and must be implemented in BPF without calling into user space. You don't actually need to implement any of the callbacks. Most will provide default fallbacks, some won't. And SHEDX provides a set of kfuncs to actually, yeah, either actually do the scheduling, or, for example, SCX BPF kick CPU will IPI a CPU, but also some helpers that are just useful. For example, a default select CPU function that will like look for an idle CPU and like that sort of stuff. Yeah, just to like as a heads up, the kfuncs will always start with SCX BPF and the callback with ops. So just so you know where we're at. All the numbers are from 7.orc5. There's a few features that are queued for 7.1 I'll mention as well. So yeah, Andrea already mentioned this queue, so I'll be relatively quick. It's like the primary abstraction, and it holds runnable SHEDX tasks. You can move tasks between those DSQs, and there's sort of two kinds of special ones that Andrea has recently called terminal. I think it's quite a nice name because you're sort of no longer on the BPF scheduler control, though that's the global DSQ and the per CPU local DSQ. That is kind of your run queue. When moving finally from a custom DSQ to a local DSQ, ShedX will handle all the tricky bits, like checking that the task being moved will actually be able to run there and migration isn't disabled. That is also, by the way, why we don't know really in the BPF scheduler if our move did actually do anything, which is a bit tricky. And moving between the DSQs and into local DSQ, that won't happen when you use the kfunc, but usually after the callback returns to just get around the locking problem. So basically locking is not an issue at all. So the kernel style locking is not an issue at all for the BPF scheduler. That is sort of the main abstraction I think that DSQs try to provide. And obviously, like, you can't really do like kernel style locking with BPF with still having the guarantees in place. DSQs can be virtual, like vtime based, but for this talk, it doesn't really matter. Just assume they're all FIFOs. Although most general purpose schedulers, of course, use some DSQs that will be vtime based. So Andrea already basically had a similar slide. There's two ways to look at ShedX, what actually happens. One of them is the easier one, which I'll start with, which is per CPU. So kind of consider the main scheduling loop, like pick next task somewhere at the end of that chain is maybe this, obviously very simplified. Whenever the ShedX gets to run something on a CPU, it will check the local DSQ, its own local DSQ. If that is empty, it will try to get one from the global DSQ. And if not, and only then, there will be a callback into BPF, namely dispatch. Dispatch can then move a task to the local DSQ, or not do that. In that case, ShedX will actually let the CPU go idle. And also the BPF scheduler will need to wake it up either in the in-queue callback or specifically using the kick CPU, kick idle. Of course, it could also be woken up by a higher scheduling class. This is sort of the per task perspective. Andrea had this as pseudocode. I tried to visualize it a little bit. So think we want to track the task state. Again, later we will talk about BPF, about PELT in BPF. So I'm thinking about what callbacks am I as a scheduler gonna receive for the different task states. So I'll get init task first, which will usually allow me to, like, for example, set up some per task storage where I can, for example, put those PELT values in. I'll also receive an enable, so it's at least like a SchedX task now. And then at every wake up, I'll go select CPU, runnable, and then in queue. In queue is actually where the sort of the placement decision is supposed to happen. And then there's I have this is the sort of running loop where the task will receive running, then it will continuously receive tick if implemented. And if its slice expires, this is actually like a CPU callback. It will obviously get dispatch. Dispatch can just refill the pref task, and then we will stay in that loop. Or the task will be stopped, and either a new one will start, or you go idle. In either case, stopping might lead to DQ and then quiescent. So quiescent is the go to sleep, and this is the parts that this is sort of the wake up block part. So maybe just a few things. So why select CPU is sort of non-obvious why it exists, and basically you can directly go into a local DSQ, and then because at that point the task isn't actually in queued for the BPF scheduler yet, so you can sort of circumvent the entire thing. In particular, if you have like per CPU K workers, there's no point in it's just a minor optimization. So you never actually go through this chain. You can avoid that. Yes, as Andrea already mentioned, in 7.1, you will actually have matching NQ, DQ pairs. You can, so this is mostly only possible since then. And like, I want to say a task is like pickable for BPF between those two, and it's runnable if it has received the runnable without having received a quiescent yet. And obviously, if both is true, then yeah, I would say that the task is then like pickable for us for a BPF scheduler. Finally, you get disable an exit task if the task exits, and yeah, technically you can go from enable and disable back and forth if the task is moved. But yeah, again, that's a bit of an edge case we won't really bother with. So yeah, looking at DSQs, this is what the kernel shed domain hierarchy looks like on the left-hand side, and on the right-hand side, I wanted to, yeah, basically it's the same thing, just like implemented as DSQs. It doesn't have to be this way. This is just like one way to do it. So just to imagine local DSQ CPU 0 is empty, then it can like go up the hierarchy, see if there's a task waiting to be scheduled in the MC DSQ 0 and go down there. So I think if that is how the BPF scheduler would work, and that's one way to implement it, to me it felt very bottom up. If that makes sense at all for you, it did make sense for me, because often the dispatch is where where a lot of the logic is. For us, dispatch, it feels like new idle balance, but it's so much more than that. That's really the core of the logic, is usually in the dispatch callback. And yeah, of course, once a task wakes up, it can just be enqueued, for example, here in the NUMA 0 DSQ without much logic. And the real placement logic then would be in a dispatch where it actually gets pulled into the CPU. Yeah, that is basically almost all there is to DSQs and as an abstraction. So if you have any questions on that, it's be good now. Otherwise, I'll move on from that. Yeah.
How do you avoid the cache line bouncing if it's a common DSQ?
Sorry?
You might have a lot of cache line bouncing, right? If it's a global thing.
Yes. Yeah. Exactly. Yeah. So I mean, that's basically your job as a schedule implementer to know which task you should directly put, maybe whatever in the MC domain, so you avoid that problem. But obviously there are some tasks which wouldn't care about that, maybe, and they can. Yeah, that's kind of the policy decision. That's the secret sauce, if you wanted to. An alternative is also there's BPF storage like maps. You can. So once you get the NQ, it's sort of your job as a BPF scheduler to make sure this task actually gets to run at some point, and you don't have to put it in any DSQ. You could actually put it in BPF storage. Just yeah, for example, yeah, have like the PID mapped in there. It's a bit more involved. Eventually, you're gonna have to use a local DSQ to get that running. If you rely only on BPF storage, but you need task state tracking yourself. So if you move directly into a local DSQ, yeah, it has to be the CPU's pointer, so affinity has to match, can't be migration disabled. That's sort of stuff. So anything that isn't that will error out. That is all your job to do. But BPF storage is mostly used, I want to say, for user space interaction, because they can't really like access DSQs. So that's how the communication works. So it is used together with DSQs, and but technically you could implement one without any custom DSQs at all. So yeah, just a bit to recap. This is what a different like NQ archetypes is what I would call it look like. I can directly insert to local from select CPU and basically never really go into the BPF scheduler custody. You can insert into global from NQ. You can do a custom GSQ and only fetch it to a local one to that dispatch callback. You can do BPF data structure plus the dispatch callback. And actually, technically, you could also, a remote CPU could be inserting into your local DSQ. That would work too. So let's look at maybe the costs of those, because these are clearly like very different code paths. ShedX, what is actually kind of nice is that obviously I can benchmark by taking very similar schedulers and implementing different callbacks. For example, first of all, the baseline is I just took fair wake up, and then I can do either directly only use select CPU and do direct dispatch. I can do implement select CPU but never actually do a direct dispatch, so I get both select CPU and NQ. I cannot implement select CPU at all. That is here, and only get the NQ callback. And actually, like a bit of a trick I used is also to get to set the affinities of the benchmark task, and I'll only get the NQ then too. So yeah, the benchmark is just like a few text two tasks, few text wait wake. They are pinned to two CPUs, not one for that trick, except for the CPUs allowed one. So basically the actual like, and these CPUs are the same. So actually the task placement decision shouldn't play a role here. There's no like better CPU to really find. What I found is actually that and again, like fair.c is quite involved in trying to find a good CPU, which it kind of won't here. So it's actually not that unsurprising that it's maybe slightly lower than not using using ShedX without using BPF, sort of, which is the full select direct, 20% more wake ups per second. It will only get select called really in the most common case. If I do both, so select CPU, it doesn't actually directly NQ. That is like a 30% hit compared to fair. If I only do NQ, that's about the same, I want to say. And if I don't implement anything, that is actually much better than what fair does. Again, like fair is just a generic baseline, because really there is no good CPU to find. And also this is technically an asymmetric system. So it's the wake up path is, the fair is just really as a comparison. I don't mean to say that like fair wake up path is worse than ShedX. This is just to see what the NQ callbacks really cost. So yes.
In the last case, you mean so you're basically loading at an empty BPF scheduler?
Yes. Okay. Practically, yeah.
So, it's the core SchedX part.
Yes, yeah.
So you're actually using the global DSQ in this case.
Yeah.
Okay. Interesting. Thanks.
Yeah, but it is basically, as you kind of hinted at, you don't have to implement anything, and that's sort of what this is measuring. It never leaves ShedX or. So let's look at task state. As I said, it's interesting both for Pelt, but also if you want to use these BPF direct inserts, so BPF storage into direct insert. So you have to get the enqueue running. The task will execute, and you sort of at the running you need to get a timestamp, which is like your, let's say, your pulse clock, or if you use wall clock time, then a wall clock time until the stopping happens. Again, you need to get a timestamp here. What's a bit special is like there's CPU release and acquire, which is when a higher scheduling class will preempt you and you sort of lose access. This is obviously time that you don't get, and you probably shouldn't be accounting for in PELT. It's like a reduced capacity. We have like a similar concept in FAIR. So if we wanted a similar concept in JX, we would need to implement those callbacks. Yeah, and of course, if it goes to sleep, we need to acquire send. Yeah, acquire and release, they are marked deprecated. So if you actually do want to use this, you need to use trace points on get switch, but it's semantically close enough, doesn't really matter. That's just FYI, because obviously you can attach also something on the trace point. So it's basically similar enough. So again, I have 3 different task states I tracked. The baseline here is ShedX actually, and I used 2 different benchmarks. One is Hackbench, and the other is StressNG CPU, which are sort of 2 ends of a spectrum. StressNG CPU never goes to sleep; it's just hogging the CPU. While Hackbench, very short-lived. Probably preemptions, that sort of stuff, wake-ups. So obviously the numbers aren't really relevant. The deltas are interesting. So the baseline is only select CPU and enqueue. And this is on so once we implement dequeue and quiescent, so to track just the wake up bits, which really isn't that useful in of itself. Already see like basically 5.5 on Hackbench and a bit more than 1 on StressNG. Surprisingly, then adding running, or more or less surprisingly, running and stopping, CPU acquire and release, that's basically free at that point. What is a bit more expensive is what I call profiling. So in particular, coming from Android, and this, let's say you want a per task profiling, seeing what it actually does. For example, read PMU counters to see what is actually happening, to then, let's say, more accurately place the tasks, the task. Then you also need tick, because you can't rely on running and stopping events itself. I actually, for this benchmark, all I'm getting is the timestamp. So I'm really only computing the running time received. But just to see what tick costs. Obviously, reading PMUs would be a bit more expensive. This is all on 250 hertz, and there has been some discussion on Android to move to 1000 hertz, so I did that too. You obviously can see that like StressNG is up to over 3.3% regression, which is definitely significant. If actually tick is rather expensive, if you don't really need it, I wouldn't. In particular, we often use tick and then only do something every 10th tick. Probably better off using a timer. In particular, if you don't need the exact tick timing. So with that, I actually come to the first case study, and of course, working for ARM, that was sort of the interesting bit. It's coming to Android. Android means probably something like PELT, or even if you use something like Volt, the callbacks are the same. What would customers have to implement? How would this look like? You need obviously the state tracking to see the running time received. That was basically already discussed. Obviously the new NQ DQ stuff with 7.1, that works. I think you really need acquire and release to track. So it doesn't your running time is still accurate, but obviously if like 50% of your time is stolen by RT, fair for that matter, but yeah, I want to say RT, then you want to know that this the CPU maybe has less capacity effectively. So yeah, and obviously all the pelt values, they will be stored in per task data storage, because otherwise you can't, you want pelt values obviously to migrate with the task, and you have to always have per run queue aggregation. What is that useful in and of itself? I think it already works quite well for CPU freak. Also thermal needs it, DTPM, but also a building block for CAS and EAS. So let's go and look at that. I think the main thing to highlight is how to implement misfit migration, because as I said, once a task is on a local DSQ and potentially it's not going anywhere from there because it keeps running, but it's too small, because it is always running on a small CPU. You want to migrate it up at some point when you realize when the pelt says the task is getting too big now. The critical point really is that it's outside of the BPF scheduler control because it's in a local DSQ, a terminal one. There's basically two ways to do that. One is setting the slice to 0, which you need to do on like a tick. Then it will go through the enqueue path, or there is actually one k-func which is probably quite often used, to re-enqueue local, which will let all of the local DSQ go through an enqueue path, which is potentially many tasks depending on how your scheduler is designed. But that's really the only way to get, for example, to place tasks that are on a run queue somewhere else. EAS, like extending capacity-aware scheduling to energy-aware scheduling, really isn't that interesting. It's mostly an energy calculation at wake up. Most of the discussion has been on how to get a hold of the energy model, but that's like a technicality, I think. So obviously you cannot use a global DSQ because it's terminal, and you will not actually get a callback when it gets dequeued from a global DSQ or from a local. So basically it's invisible to you and it can run wherever. You absolutely don't want that to happen. Yeah. That's pretty much it.
Yeah, I was going to ask about this EAS implementation.
Mm-hmm.
So we already have some race condition when we choose different CPU.
Yes.
Sometimes from one CPU is kind of distorted.
Yeah.
And here, if you add yet another layer of abstraction, and then you said that you cannot fully trust if the task is already moved.
Yeah.
Is it not painful for estimating the energy at runtime for many CPUs at the same time?
Right. So I mean, especially with the fact that is a good question, and I have that up in the discussion. So especially with the re-enqueue local, which is actually quite, you probably want to call that quite often, as in re-enqueuing everything. That does mean you call the wake up path, the enqueue path quite often, and that does potentially mean it will be called from many CPUs at the same time, which means your per run queue or per local DSQ or per CPU aggregations and calculations, which are EAS is based on, are stale. But I mean, the risk is, I think, now higher, but at least, I mean, as far as I know, our experiments really, I mean, this is a theoretical issue. I think it's good to be on top of that, to be acknowledging that this exists and checking if this is an issue, but I didn't find that this is now doing much worse energy-wise, but I didn't do too much like power comparison. I just wanted to see, is ShedX, like, are you able to write something like EAS, and how expensive, how much is the overhead, not necessarily how accurate are the decisions made by it. But it's definitely another point you would need to look at.
the re-enqueue local. So we also have iterators, and potentially you can iterate to the local DSQ
Yeah.
and move the target task somewhere else.
Yeah.
But I'm afraid like it's probably more expensive than just doing it.
Yes. Yeah.
So I don't know actually.
Yeah.
That's another option.
So to be honest, I mean, my personal experience, I don't have like, it's hard to back that up, but I always found like also re-enqueuing local gives you some sort of assurance that you are actually on top of all the tasks, because you really don't see them otherwise if they don't go through the re-enqueue.
You can iterate all of them, and if you iterate all
but
of
it's them, right, but it's race. Yeah, I mean, depending. Yeah.
and
potentially
there's
racing
not involved, so
yes,
it's more expensive.
Yeah.
That's why.
Okay. Yeah. Any further questions on that? Because then that one is going to be a little bit different. Yeah. Core scheduling. If you're not familiar with the concept, it's like basically security. SMT is like a side channel attack. So use case is kind of, let's say you're running a server, different customer. You don't want to disable SMT altogether, but you are aware of the security implications, of the potential security implications. So you only want the same customer VM vCPUs scheduled on SMT siblings. The kernel does provide infrastructure for that, but yeah, this is about the BPF implementation that works exactly the same. You have like all tasks are assumed to be trusted cookie 0, and then any other cookie is assumed to be non-trusted, and they have to be equal. That means dispatching to a local DSQ. Dispatching to a local DSQ is tricky, or actually assigning that, because you need to IPI the sibling and also do like a bit of reservation, like, oh yeah, I wanted this cookie now, then, and then IPI and see if that reservation didn't raise with a reservation on the other one. So you need like BPF spin logs. It's potentially quite expensive, but that's like besides the point. Also you need to potentially force siblings idle, but that's just, I mean, that's how core scheduling works. If you don't have an appropriate twin task for a sibling, then you need to force idle. I implemented this basically with the DSQ per cookie class, and then all in dispatch. What I noticed, because ShedX specifically provides this S6 kick weight, which is actually basically the only callback that will the only k-func that will execute during the callback and like wait for the result. So when it returns, the IP, like the remote CPU will have been preempted. So it's marked specifically for core scheduling, but it didn't work at all until last week. It completely deadlocked the system, but it works now. And yeah, you have to use it in dispatch before actually like marking the cookie task reserve.
You're the only user.
Yeah, I'm the only user now, apparently. Yeah. Any questions on that? I have like a. Maybe actually I'll maybe get back to gang scheduling. It's a bit of an interesting one. I'll probably get back to that. What I found really cool though, what really sort of sold it to me is seeing. So Andrea upstreamed the DL server, which was already discussed, and like just stopping and starting it for X and fair, that uncovered some issues, and he actually has gone and written the self-tests. And ShedX has a lot of self-tests, much more than the scheduler does. I think it's just one, the scheduler for core scheduling. And I thought, why is this so cool? Because basically when we do scheduler testing also at ARM, it's usually involving like a lot of C group and affinities, and you try to create scenarios, like specific edge cases, and see the result. And you sort of hope they happen, and you increase the likelihood by doing affinities and so that sort of stuff. But actually the self-test in PF can be much more deterministic, because you're supplying both the workload and the scheduler. So you can actually specifically create those scenarios. You already discussed mode partial, where you don't move any tasks to X and keep fair enabled, and then user space has to set move them to X specifically. is actually quite nice. I use it for something like the pelt testing, because you can actually, you must account obviously for the stolen time, but other than that, you can just have 2 tasks in Ext, and then you can, if I move this task now here, the aggregate needs to be exactly this, because there's no other, I know all the tasks, no K-workers, nothing. Makes testing a lot more predictable and therefore also powerful. So yeah, what is this actually useful for apart from testing my pelt in BPF? Obviously, anything that is shared between ShedX or class X and the other classes. I did some wake up and in queue behavior testing that is in core scheduling, sorry, core part of the scheduler. But I wasn't really convinced that failing one of those tests would actually result in a booting system. Like if the wake up of other tasks doesn't work, that's kind of pointless. I did though, because the core scheduling I mentioned, the in-kernel variant is actually also active. Well, it respects all of them. So you can actually load a BPF scheduler, use the kernel core scheduling implementation, and then sort of go hunting for violations. You can kind of see, oh, this CPU has currently cookie 3. Let me try to schedule cookie 4 on its sibling. And therefore, you don't have to hope for these scenarios to happen. I have an extensive self-test or extensive self-tests written for that. Unfortunately, they didn't discover any issues, which is a bit disappointing. I would still upstream it because I think it actually does provide coverage. And obviously, future candidates could be maybe also proxy execution, where you can really create these nasty scenarios that we really don't have a good way of provoking otherwise. I think this is quite cool. What I thought with the pelt implementation is just very painful. Maybe we can provide something in the kernel, maybe just util average, because that's pretty straightforward. And yeah, it's more or less directly derived from running time and scaled and that sort of thing. Also, of course, also UTS, if you the wake up, like when tasks wake up, that's not a BPF scheduler decision really. Also maybe, yeah, runnable, it's debatable, but load assumes a lot of scheduler behavior. We can't probably, it's not obvious about how you could provide load to the kernel without basically looking into, or yeah, assuming anything about the BPF scheduler behavior. I think also the CPU acquire and release is a bit nasty. You could probably just track that in the kernel, how much time was stolen from you. If we do implement just like even util average, util S, that would already probably be enough to do something with CPU freak. Just provide an out of the box thing. And what I think would be really nice, obviously, is the point I mentioned before. We could do some really cool, first of all, runtime validation. So at all the callbacks, you could see, does my snapshot of the system actually like basically use my BPF implementation and check that against what the kernel is providing. And if there's any mismatches, then it's bad, right? Because we're looking at a snapshot that should match up. But runtime validation, we could also just do at like the traces, basically, if we do extensive tracing. But these specific scenarios, that's really where this would shine actually for coverage, I think. So yeah, again, like if you place those sort of experiments that also Pierre mentioned, if you let them share a run queue, how do the pelt signals develop, that you could write very specific tests for that you would require to pass. So yeah, I mean, I'll do the summary and discussion now, and then probably get back to gang scheduling if there's, depending on how much there is. I think honestly, I struggled a lot with. So this was quite easy because I've just presented the solution, but I think capacity-aware scheduling and energy-aware scheduling is quite hard, and the measurable, like the overhead will be measurable, will be visible. I don't know if they're willing to accept, like if Android vendors are willing to accept that, but I'm happy to be proven wrong here. I found the re-enqueuing of the entire local DSQ, I already found a bit weird. Maybe there's a better solution there. I don't want to propose too much. although we can discuss something. What I also found a bit weird is like the global DSQ, because the global DSQ is also used by sort of the core ShedExt, and it doesn't know what to do with the task, because what you requested basically isn't anymore a legal operation. So yeah, maybe introduce a flag to just disable the global DSQ. At least like it wouldn't make development a bit less painful. What I found particularly a bit strange is, I mean, you don't have any locks, and that means when you're preempting a remote CPU, you have actually no idea what you're preempting. Which, for example, in the gang scheduling case, that basically means I only want to preempt the gang task. So I'm preempting a remote CPU, and then now the remote CPU needs to check, was I actually preempting a gang task, or have I just preempted a K worker? And if it was a K worker, I need to keep running that K worker and actually make sure that the gang task I wanted to preempt is being preempted. So maybe there's a better API. Maybe we can just remove a specific task from a local DSQ, something like that, either with a CPU given, or maybe just globally, like I want this task to go through the re-enqueue. I don't know. I also, I think Peter already mentioned that, but retiring APIs, I think ShedExt could be a bit more liberal with, because it's not a stable API. So, for example, local on insert from anywhere, but in queue is this BPF storage thing is technically possible, but so far no one was even theoretically able to implement that, because the callbacks wasn't there, the semantics wasn't there, and I still think it's racy. I was not able to implement that working, and I haven't seen a working implementation. My claim is you can't do it. Why is it supported then? Like, why don't we just say local on inserts, you need to be an NQ or select? It would make it, like, it would also make it a lot more clear, like how to construct a scheduler. Also, this SCX kick weight, I was a bit surprised that Tejon didn't just drop the thing altogether, because clearly no one's used it. And sort of my provocative question would be, can we, as like the regular scheduler developers, maybe get something out of ShedExt being mainline, namely what could be well tested with ShedExt-based self-tests that actually have not only test the ShedExt infrastructure, but more general case like the core scheduling or proxy execution or a pelt if it will be provided for ShedExt, that sort of stuff. Yeah, any questions? Any discussion?
Can you expand on how? I think I'm missing one detail. How do you plan to test the let's say SCADFAIR using like putting together SCADX scenarios to actually then test the?
So you can't do anything. That is, so for example, PELD, which is now currently only in FAIR mostly. You can't test that because it's not available to you. That's why I'm saying if we were to make some of that, like the util average part, available to X tasks, ShedExt.
Available like replicating the implementation, or
while moving it to core, and therefore
then you can test it.
Well, I mean, PELD is pretty straightforward because you only have to. I mean, it's already rather generic. You only have to get the calls right, the entry points.
For example, you mentioned proxy execution, like to create scenarios to test. I know.
Yes, so that would need to be like a shared implementation, and you only test it through the class X.
Okay, so. But
yeah, I mean, the assumption is of course that you can get a decent coverage for FAIR as well because it's the same implementation.
Yeah. Okay.
But yeah, also here, like maybe there's something obvious that I didn't see that could also be tested. I chose like core scheduling and proxy execution, but maybe there's other stuff that anyone could think of. Yeah, apart from that, I'll go back to gang scheduling, which is, yeah, okay, yeah, I mean, real quick then. Gang scheduling it's kind of similar to core scheduling, except it's not security oriented. You actually like only you assume only the task will only make progress if all of the gang actually makes progress. So yeah, basically, it's kind of similar, but what is a bit awkward that you don't know if your insert actually, if your moves did anything, if any of them went wrong. That's a bit awkward because you provide a mapping at the start, and if any of them fail, you would need to revert that mapping. And yeah, of course, you can't lock any run queues, so you have to do it sequentially and like revert the entire thing. As I already mentioned, you have no idea what is being preempted. That makes it additionally awkward. 7.1 actually brings a new flag, which is S6 NQ immediately, which will, if it wasn't successful, go through NQ again. So you don't get a feedback immediately when you call it, but at least you see the NQ, and you avoid the global DSQ. I think and there is actually a flag to always use NQ immediately, which almost is the same as disabling a global DSQ. So that's almost kind of what I wanted to ask for. Yeah, just a bit to reiterate how like this gang switch would look like, and yeah, basically you have to see if you decide the mapping here for 8 tasks, do all the NQs. If you got an NQ callback for any of them, then you must assume that the gang switch wasn't successful, and revert here and try again for a different mapping. And if it worked, then the gang switch commits. It's kind of high overhead in case it doesn't work, but I mean, it's gang scheduling. It's kind of assumed. Yeah, I mean, that's it. If anyone has anything on those, I'd be.
Okay, so the was this one what you were? Oh yes, like to disable global DSQ. And there was also the fact that you can't do a local on DSQ. I think the patch that is posted on the list, but I never had the time to complete that. Was the one that was basically transparently solving being able to use local on this patch. So if that is completed and it's applied, it would implicitly never use global DSQ, because global DSQ is the fallback, right? When there's an affinity mismatch or disabled mismatch. So maybe we should just work on that, and if we merge that, it would solve both of your issues here.
I'll go take a look.
So
if anyone doesn't want to get involved in ShedX but has an idea of what to get testing wise, I mean, please reach out. I'm happy to write the BPF part. If you have a scenario in mind, we could test. Yes.
So your comments with respect to testing. So the idea is that you just place the tasks in some configuration that you found to be unpleasant, and then let the scheduler.
Right. Yeah.
How do you come up with those placements of tasks?
I mean, this is like the scenario I want to test for. For example, with a Pelt implementation.
How do you find the interesting scenarios that you want to test?
Thinking about them. For example, in Pelt, I want to know, okay, if a task migrates from CPU 0 to 1, I want its util, I want to be the aggregate util here to be less by the amount the task has, and that now being on CPU 1, and that sort of thing I can create. And of course I can do that with multiple tasks or whatever. But yeah, you would need to think of scenarios, edge cases, or test cases basically. But my argument is that you can be a lot more powerful in what you actually implement. If that answers.
If you're trying to, you see executions of applications and you find that the behavior is unpleasant, and then save those scenarios as things you want to test forever in the future, but then they might not be relevant anymore.
Yeah, maybe. I mean, currently almost any coverage would be an improvement, because there's no self-tests at all due to yeah, you can do trace-based evaluation, but that's like a bit finicky.
Right, thank you.